Okay guys, in this video lesson we're going to tackle this idea of when reactions reverse on themselves. Or basically, what happens when a reaction runs, but then as you start to make products, you can also reverse that and the products turn back into the reactants. Okay, so when that happens, we call that a reversible reaction. Okay, what we say is that the reaction is actually going to run simultaneously in both directions. Now, to indicate that both directional kind of pathway, we have a double-headed arrow here. Okay, so in this scenario, our sulfur dioxide gas and oxygen gas can react to make sulfur trioxide gas. However, sulfur trioxide gas can also break apart and make these two things. Okay, now taking a look down here, this kind of gives you an idea of what's happening here. So we have, some sulfur dioxide, some oxygen. Here you have all sulfur trioxide. In the middle, you have a little bit of both. You have some sulfur trioxide, you have some sulfur dioxide, and you have some oxygen. Okay, so in the case of a reversible reaction, okay, if it was all of this stuff or all of this, we would not have equilibriums. Okay, when you have a reversible reaction, you have some sort of equilibrium between all three things. So at any given point in time, there's some of this, and some of this all in the reaction. Okay. Now, with this, we got to be kind of careful about looking at amounts versus rates. Okay. So as a reaction runs, they don't need to have equal amounts. Okay. So it doesn't have to be 1/3, 1/3, 1/3, or half and half. Okay. It has to be some of each one. So these double-headed arrows, it doesn't have to be a half and half scenario. It can be favored on one side or the other, but there will always be some of everything present when you have a reversible reaction. Okay, we're going to switch clips here now with a little demonstration that kind of helps us with that idea. Okay. Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, some green water here. That represents our reactant side of our process. And then, of course, we have our empty container over here that represents our product side of the process. So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now if I continue to scoop like this and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here, and I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay, so the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay, so if we go back to the graph on our slide, we would see that this is the first one, or the top one, where the rate flatlines and becomes equal. Okay, now it doesn't mean that we have to have equal amounts. If we look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you'd almost get the indication that maybe the amount in each side has to be equal. So it has to be 50% this, 50% that.
And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay, so in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay. Now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which means if I pour 140 into here, and I pour 140 into here, there's no difference, okay? So I am now at equilibrium, okay? So switching again, I can do this all day long, and from this point on, there will be no change in the volume in either tub, which means this reaction from reactant side to product side is at equilibrium. Okay, I can just keep right on doing it and nothing changes here. Again, we have 140 plus. This particular scoop happens to be actually less in terms of what we have. Okay, it's not perfect with using scooping water. But again, we see 150 to 140, same amount of volume crossing over equilibrium. Okay, now in this case, if we look, we had equilibrium, so the process is at equilibrium. But if we look on the product side, we have much more water than we do on the reactant side. Okay, so in this case, because we end up with more product, we would call this a product favored equilibrium. We have less reactant, so it is not reactant favored. Okay, if you flipped it, and if you had a scenario where at the end you had something like this, this could be an equilibrium. It might mean you're using the big beaker for the product side and this little guy for the reactant side and scooping over and over again. If that was the case, if you have very little product and a lot of reactant left over, this is a reactant favored equilibrium. Still at equilibrium, still flatlined, but we have no change in reaction rate there. Okay, so if we go back to the idea of the graph in our notes again, we see the bottom graph shows the amount, and in that graph, reactants were in red and products were in blue, I believe. So that was a product favored. So let's reset that to look like product favored, where once you've reached equilibrium, the rate of transfer, or how much gets transferred across, again, our rate of transfer would be equal. So that would come together on the graph, but yet the amount of product would be more than the amount of reactant. At equilibrium, this would be product favored, which represents the second graph in that slide. Okay, guys, that's the demonstration for this. We'll go back to our notes now. Thank you.
Okay, so if we keep going on this idea of reversible reactions, one thing we want to be aware of, that in either direction for this reversible reaction, we still have activation energy. Okay, so for example, if we take glucose and react it with oxygen, we had to go up and over activation to make the reaction proceed to make carbon dioxide and water. Okay, we call that the oxidation of glucose, or cellular respiration. If we go the other direction, where we take water and carbon dioxide, we can get this reaction to run in reverse, but we have to give it all of this energy to get over top that hump to go back down here to make glucose and oxygen, okay? Otherwise known as photosynthesis. So here's another example from the biological world where we do have a reversible reaction, and in our bodies and in plants especially, we need to have both these things possible because photosynthesis is needed to generate the glucose, and then later in the process for plants, they need to take that glucose and utilize that as energy source, okay? So we need to have that thing be able to go in both directions, so for a reverse reaction. But the take home is that both directions need to go over top of that same activation energy as we run, okay? Now, in the demonstration, we had this slide up a lot, and the whole point of the slide is to remind ourselves that when we have things that are at equilibrium, okay, we want to make sure that we bold, italicize, highlight, underline that both the forward and reverse reactions take place at the same rate. I can't emphasize this enough. It's the same rate. It does not mean equal amounts, okay? If we look over here, if we graph rate versus time in a reaction, the purple represents equilibrium. It's when you have a flat line. So you have equal rates. Down here, if we graph the amount, when the flat line hits, we have equilibrium. The amounts don't change, but they're not equal to each other. So in this case, because we have more products than reactants, this would be considered product favored equilibrium. Okay? If we had a scenario where we had our reactants come down and we had our products come up, and they flatlined like this, where we now have equilibrium in this area, we're still equilibrium, okay? We still have no change in amounts. Our rate would be the same, but again, in this case, we would be reactant favored. Because our reactants, which is represented by the red, is more than our products. Oops. Products here. Okay? So we want to make sure that we're aware of that the rates become equal, not the amounts, as we do this. All right? Now, when you're working with equilibriums in those positioning, we actually can calculate this position. We do that by a constant value called K. Okay? So K can tell us this position, basically if it is product favored or if it's reactant favored. All right? That expression we always represent is K equals products divided by reactants. Now, if it was perfect, half and half, it would be product concentration over reactant concentration. You'd have a K value of 1. Okay? However, if you are product favored, you end up with a very large K because product is in your numerator. So here's an example of a product-favored reaction where majority of the particles in here turn to products. Very little are reactant. Over here, we have an example of a small K, okay? So we're going to use K values a lot in the upcoming days in terms of measuring for equilibriums. Just keep in mind that anytime you have a constant for equilibriums, if it's greater than 1, it's product-favored. If it's less than 1, it's reactant-favored, okay? They can't go negative, because we just have a relationship between the concentration of products over the concentration of our reactants. So they can't go negative, but you can approach 0. So if you have a reaction that approaches 0, okay, so essentially we're making no product. Eventually, if it's so reactant favored that it's almost 0, it doesn't really react. Okay? If you have a constant that approaches infinity, where it's almost 100% product and no reactants, then we would say that that reaction is not reversible, okay? So the closer it is to 1, the more reversible it is in terms of products versus reactants, okay? Now, 1's ideal. I don't know of any reaction that has a constant of exactly 1 where it's 50-50. It always seems to be 1 is favored over the other. That's pretty normal as 1 gets favored over the other one, okay? All right, so to wrap up this video now, we want to take a look at this idea of reversible reactions and their equilibriums and make sure we can start to point out these positions a little bit better. Okay? Now, when we deal with the position, we wanted to talk about if the products have a larger concentration versus the reactants. Okay? One way we can represent that is by using non-equal arrows. Okay? If you ever see a long arrow towards the products and a short little arrow back, they're trying to tell you this will be product favored. If you see a long arrow back and a short arrow to the front, you know it's reactant favored, okay? So when it comes to these equilibriums and these positions, again, we're not talking about equal amounts, we're talking about equal rate of transfer, but you do have a no difference in amount when you're done, okay? In terms of B will stay the same, A will stay the same, even though the reaction continues to run, the transfer is the same, so there's no change in your amounts anymore, right? One thing to highlight, one thing we want to note and make sure that we are aware of, catalysts do not affect the amount of reactants or products present. Okay? Quite often I get students who give me this misconception. They think that a catalyst can make something more product favored, or a catalyst can keep something more reactant favored. That's not true. All catalysts do is get you there faster. Okay? It's like having a faster car. Okay? Just because you have a faster car, you drive faster, doesn't mean the distance between your house and Fort Lauderdale, Florida is shorter. It just takes you less time to get there if you drive faster. Okay? So again, make sure you highlight this and make a note of it. Catalysts do not affect amounts. They only get you there faster. All right, guys, we're going to end the video here. In our next segment, we're going to start actually talking about quantifying this and getting some numbers to it. Thank you.